This justifies why researchers should never outpace speed of light. In 2011, the Opera experiment mistakenly observed neutrinos appearing to travel faster than light. Even before the source of the error was discovered, the result was considered anomalous because speeds higher than that of light in a vacuum are generally thought to violate special relativity, a cornerstone of the modern understanding of physics for over a century. Welcome to our channel Space Venture. In today's video, we're going to talk about the speed of light. Opera scientists announced the results of the experiment in September 2011, with the stated intent of promoting further inquiry and debate. Later, the team reported two flaws in their equipment setup that had caused errors far outside their original confidence interval. A fiber optic cable attached improperly, which caused the faster-than-light measurements, and a clock oscillator ticking too fast. The errors were first confirmed by Opera after a Science Insider report. Accounting for these two sources of error eliminated the faster-than-light results. In March 2012, the co-located Icarus experiment reported neutrino velocities consistent with the speed of light in the same short-pulse beam Opera had measured in November 2011. Icarus used a partly different timing system from Opera and measured 7 different neutrinos. In addition, the Gran Sasso experiments Barricino, Icarus, LVD, and Opera all measured neutrino velocities with a short-pulsed beam in May, and obtained an agreement with the speed of light. On June 8, 2012, CERN research director Sergio Bertolucci declared on behalf of the 4 Gran Sasso teams, including Opera, that the speed of neutrinos is consistent with that of light. The press release made at the 25th International Conference on Neutrino Physics and Astrophysics in Kyoto states that the original Opera results were wrong due to equipment failures. On July 12, 2012, Opera updated its paper by including new sources of errors in its calculations. They found agreement of neutrino speed with the speed of light. Neutrino speeds consistent with the speed of light are expected given the limited accuracy of experiments to date. Neutrinos have small but non-zero mass, and so special relativity predicts that they must propagate at speeds lower than that of light. Nonetheless, known neutrino production processes impact energies far higher than the neutrino mass scale, and so almost all neutrinos are ultra-relativistic, propagating at speeds very close to that of light. The experiment created a form of neutrinos, muon neutrinos, at CERN's older SPS accelerator on the Franco-Swiss border, and detected them at the LNGS lab in Gran Sasso, Italy. Opera researchers used Common View GPS, derived from standard GPS, to measure the times and place coordinates at which the neutrinos were created and detected. As computed, the neutrinos' average time of flight turned out to be less than what light would need to travel the same distance in a vacuum. In 2 weeks up to November 6, the Opera team repeated the measurement with a different way of generating neutrinos, which helped measure the travel time of each detected neutrino separately. This eliminated some possible errors related to matching detected neutrinos to their creation time. The Opera collaboration stated in its final press release that further scrutiny and independent tests were necessary to confirm or refute the results. In a March 2011 analysis of their data, scientists of the Opera collaboration reported evidence that neutrinos they produced at CERN in Geneva and recorded at the Opera detector in Gran Sasso, Italy, had traveled faster than light. The neutrinos were calculated to have arrived approximately 60.7 nanoseconds sooner than light would have if traversing the same distance in a vacuum. After 6 months of cross-checking on September 23, 2011, the researchers announced that neutrinos had been observed traveling at faster than light speed. Similar results were obtained using higher energy neutrinos, which were observed to check if neutrinos' velocity depend on their energy. The particles were measured arriving at the detector faster than light by approximately 1 part per 40,000, with a 0.2 in a million chance of the result being a false positive. Assuming the errors were entirely due to random effects, this measure included estimates for both errors in measuring and errors from the statistical procedure used. It was, however, a measure of precision, not accuracy, which could be influenced by elements such as incorrect computations or wrong readouts of instruments. For particle physics, experiments involving collision data, the standard for a discovery announcement is a 5 sigma error limit, looser than the observed 6 sigma limit. The preprint of the research stated, the observed deviation of the neutrino velocity from C would be a striking result pointing to new physics in the neutrino sector, and referred to the early arrival time of CNGS muon neutrinos as an anomaly. Opera spokesperson Antonia Ariditato explained that the Opera team had not found any instrumental effect that could explain the result of the measurement. James Gillies, a spokesperson for CERN, said on September 22nd that the scientists were inviting the broader physics community to look at what they did and scrutinize it in great detail, and ideally for someone elsewhere in the world to repeat the measurements. In November, Opera published refined results where they noted their chances of being wrong as even less, thus tightening their error bounds. Neutrinos arrived approximately 57.8 nanoseconds earlier than if they had traveled at light speed, giving a relative speed difference of approximately 1 part per 42,000 against that of light. The new significance level became 6.2 sigmas. The collaboration submitted its results for peer-reviewed publication in the Journal of High Energy Physics. In the same paper, the Opera collaboration also published the results of a repeat experiment running from October 21, 2011 to November 7, 2011. They detected 20 neutrinos consistently indicating an early neutrino arrival of approximately 62.1 nanoseconds, in agreement with the result of the main analysis. In March 2012, an LNGS seminar was held, confirming the fiber cable was not fully screwed in during data gathering. LVD researchers compared the timing data for cosmic high-energy muons hitting both the Opera and nearby LVD detector from 2007 and 2008, 2008 to 2011, and 2011 to 2012. The shift obtained for 2008 to 2011 period agreed with the Opera anomaly. The researchers also found photographs showing the cable had been loose by October 13, 2011. Correcting for the two newly found sources of error, results for neutrino speed appeared to be consistent with that speed of light. On July 12, 2012, the Opera collaboration published the results of their measurements between 2009 and 2011. The difference between the measured and expected arrival time of neutrinos was approximately 6.5 plus minus 515 nanoseconds. This is consistent with no difference at all. Thus, the speed of neutrinos is consistent with the speed of light within the margin of error. Also, the reanalysis of the 2011 bunched beam rerun gave a similar result. The Opera team analyzed the results in different ways and using different experimental methods. Following the initial main analysis released in September, 3 further analyses were made public in November. In the Wayne November analysis, all the existing data were reanalyzed to allow adjustments for other factors, such as the Sagnac effect in which the Earth's rotation affects the distance traveled by the neutrinos. Then, an alternative analysis adopted a different model for the matching of the neutrinos to their creation time. The third analysis of November focused on a different experimental setup which changed the way the neutrinos were created. In the initial setup, every detected neutrino would have been produced sometime in a 10,500 nanoseconds, which is 10.5 microseconds range, since this was the duration of the proton beam still generating the neutrinos. It was not possible to isolate neutrino production time further within the spill. Therefore, in their main statistical analysis, the Opera group generated a model of the proton waveforms at CERN, took the various waveforms together, and plotted the chance of neutrinos being emitted at various times. They then compared this plot against a plot of the arrival times of the 15,223 detected neutrinos. This comparison indicated neutrinos had arrived at the detector 57.8 nanoseconds faster than if they had been traveling at the speed of light in a vacuum. An alternative analysis in which each detected neutrino was checked against the waveform of its associated proton spill, instead of against the global probability density function, led to a compatible result of approximately 54.5 nanoseconds. In addition to the 4 analyses mentioned earlier, September main analysis, November main analysis, alternative analysis, and the rerun analysis, the Opera team also split the data by neutrino energy and reported the results for each set of the September and November main analysis. The rerun analysis had too few neutrinos to consider splitting the set further.